So please someone answer. So can they see the screen? Uh, yes, I can see the message, but so. So, can you not unmute yourselves? No, I can't hear anybody. Okay, I guess then we have to, communicate through this chat box. Yeah. So, I'll be start the problem solving session now. So I hope you all can see the screen. So this is the first page. So I am Amurto Shah, a PhD scholar from IIT Kanpur, and I'll be conducting this weekly problem solving session on this Advanced Engineering Mathematics course. So is everybody familiar with this, with the concepts that has been taught in the first week? If anyone is not, please write that in the chat box. Okay, I guess all the people who are present are familiar with the concepts. So let us now go to the problem. So consider this first problem. Okay. So I hope you have seen the assignments for the first week, right? Which is due on 10th of August, I guess. So this is one of the problems. So I guess this was the first problem. So if consider a function that is given like this. So please follow the pointer. Okay. So that is given like this. So this is a piecewise function. So here rj is the real part of z. Okay. And so we want to examine its continuity and differentiability. So to examine the continuity, we usually employ the epsilon delta method. But here we can see that we can do better, because so first let us write this explicitly in real and imaginary form, so that we have this fxy. Okay, straightforward. So quickly, so before going in further details, we can quickly see that the power of the polynomials in numerator and denominators are the same. So here it's x squared plus ixy divided by x squared plus y squared. So the powers are same. So we can immediately see that if we blindly substitute xy equals to 0, 0, then we run into trouble. So because then we get the 0 by 0 form. So obviously in single variable calculus, we then usually employ the L'Hospital rules. But here, let us see what can we do. So straightforwardly, so this is 0 by 0 form, and we suspect, everyone's joining. And we suspect because they have the same power, same ordered polynomials, then this 0 by 0 form, after suitably taking the limit, may have some finite value. So let us, just to consider, so let us randomly choose a path along which we will approach this 0, 0 point. So remember, here now we are in the xy plane, so we can approach this origin from any direction we choose along any curve. So let us randomly choose this line y equals to mx. So if we substitute this and so yeah, as I said, usually while calculating, while examining continuity, we employ the epsilon delta method. Yes, we employ the epsilon delta method, and this is the starting point. So consider this equation. So please follow the pointer, and if we go along the above said line y equals to mx, so we'll see that the left hand side has this value, this m dependent value. So you see, if it were to be a true limit and if it were to be a truly continuous function, then this thing, this fxy minus f00 thing had to be independent of this arbitrary parameter n, but here it is not the case. So we get a limit, so that is dependent on the path. So that is, that immediately rules out any possibility of the continuity of this function fz. So yeah, so in conclusion, fz is not continuous at z equals to 0. But you can examine at any other point fz is continuous using this epsilon delta method or any other thing. So yeah, so that was the first part, and now we would like to look at the differentiability. So for the complex functions to be differentiable, and we have fz equals to u plus ib. So as we have been taught, so for this function to be differentiable, we have to have the partial derivatives with respect to x and y of these functions u and v have to be continuous. Their limit has to be well behaved, they have to be continuous, and after that they have to satisfy the Cauchy-Riemann conditions. So these are the three conditions. So explicitly we see that from this fxy equals to this explicit form. So we have this uxy and this vxy. So now, let us we have to check all the four partial derivatives separately. So let us first choose to examine this partial derivative. So partial derivative of u with respect to x at point 0, 0. So this is the definition of partial derivative with respect to x, and then after substituting and comparing this given value of f at point 0, okay, yes, and comparing this value at the origin, we get that this is the limit h tends to 0, 1 by h. So we immediately recognize that this limit doesn't exist. So the ux at point 0, 0 doesn't exist. So even though the students, the audience can check themselves that all the three other partial derivatives exist, they are well behaved at 0, 0, and moreover all of them vanish. But that will not matter here, because we have seen that the first one is undefined itself. So the limit doesn't exist, and this fz is not differentiable at z equals to 0 for this reason. So since ux doesn't exist, so there is no point to talk about this Cauchy-Riemann conditions. So in conclusion, we have this fz is not continuous and not differentiable at z equals to 0. So yeah, this concludes our first problem. So if you have any question, you can write that in chat box, or I'll move on to the second one. yeah, so let's move on to the second one. So the question is, suppose we have given some function fz which has this following u plus iv form. So we have been assigned the task to find the points where fz is differentiable, and at those points we have to find the derivatives of fz. So this is the problem. So as I said before, so for a complex function to be differentiable, what are the criteria? So it has to be continuous. The four partial derivatives with respect to x and y, they have to be well behaved, and those limits have to exist, and then those partial derivatives have themselves to be continuous, and then finally they have to satisfy the Cauchy-Riemann criterions. So we begin by looking at this uxy and vxy. So from the question we can easily recognize them, and then so continuity of uxy and vxy are no problem because these are polynomials and they are everywhere continuous. So they are continuous. So then now since they are continuous, we have no problem in taking their partial derivatives. So straightforwardly we get their partial derivatives. So the four partial derivatives are listed here. So, and from these forms we immediately recognize that the partial derivatives themselves are also continuous because they are again polynomials and no problem with continuity. So the only remaining criteria now is to satisfy the Cauchy-Riemann condition. So now we'll examine that. So yeah, and from these derivatives we see that Cauchy-Riemann conditions are ux equals to vy and uy equals to minus vx. So as we have been taught, so we see that ux equals to vy, this condition is trivially satisfied for any point. So now let's move on to the next criterion. So that is uy equals to minus vx. So comparing from here, we see that we get this equation. So we are left to the conclusion that only at the points which have y equals to 0, the Cauchy-Riemann condition is satisfied. So the Cauchy-Riemann, well, so am I supposed to give this tutorial session in English or Hindi? I'm not sure. So what have you guys been told? I mean, आप लोगों को क्या बोला गया है कि हिंदी में होना चाहिए, इंग्लिश में? Yeah, okay. So yeah, so I can't then really help. Yeah, sorry about that, Rakesh. Yeah, so let's continue. So yeah, so what was the last point? Yeah, so only at the point, comparing this criterion uy equals to minus vx, we see that the only at the points where y equals to 0 are the Cauchy-Riemann criterions are solved. So we conclude that fz is differentiable only along the x-axis where all points are y equals to 0. So then we'll now take simply the derivative. So we know that the derivatives is defined as ux plus ibx, and then trivially from substituting this, we have calculated the partial derivatives beforehand. Substituting this, we get this answer 2z minus 3. So yeah, this was a straightforward problem. And yeah, actually we should write here, so 2z minus 3i at points y equals to 0. But yeah. Yeah, no, that is not the case. So regarding the question of Karthik, so no, we do not take partial derivative with respect to x because it is only, no, that is not the case. So partial derivative, as you guys have been taught, so they are defined like this one. So consider this thing. So ux at point 0, 0. So this is the definition of partial derivative with respect to x at point 0 comma 0. So it has, so before calculating the partial derivatives, we do not know whether it is defined at a particular point or not. So only after using, only after employing this definition from then taking limit, we can conclude whether it is defined or not, continuous or not, these things. So you should start from this definition of partial derivative. So this is given for partial derivative with respect to x. Similarly, you can use the partial derivatives for y also. Similar definition. Okay. And regarding the question of Kirti, so you requested me to go to the previous page. So yeah, so can you please write your doubt? Yes, page 3. Sorry. Which one? I mean, regarding problem 1 or 2? Yes, problem 2. Yeah, so this is the page 3. So, yeah. Is it resolved? Okay, thank you. So, yeah, so that was a pretty straightforward problem. And then now we would like to move on to the third one. So, this is like a proof. So, you have to show this, given the left hand side this, the right hand side is this one. So again, this r of fz is real part of the function fz. So the complex function is, as we said, u plus ib. So r of fz means u xy. So yes, so we have to take the, this operator is called the Laplacian. So this del partial derivative twice with respect to x plus with respect to y. So this is called the Laplacian. So you have to take the Laplacian of this real part of fz and show, and see where it leads us. So yeah, let us. Okay, so let us start. So the first step is, as I said, uxy, and then from this step we will be using the chain rules. So del x2 means we have to derivative twice with respect to x. So first consider the first term. So after derivative with respect to x once, we get this 2u ux, and with respect to y once, we get this 2u uy. So this is nothing but the simple chain rules, but this time it is for partial derivatives. So for ordinary derivatives and partial derivatives, the chain rules are same. So nothing, just use the knowledge of single variable calculus. So okay, and then now we'll do the remaining derivatives. So we'll be taking the derivative for the second time. So what we get? So del x of ux, so this gives ux square and then uxx. So this thing, and taking the derivative with respect to y, we get we get this uy square and then u multiplied by uyy. So I have jumped a step. You can convince yourself that this is indeed the case. So if there is any question, feel free to ask. Okay, I guess things are okay. And then we recognize that this ux square plus uy square. So from the Cauchy-Riemann equation, we know that uy square is minus vx square. Uy is minus vx. Okay. So then uy square is equal to vx square. So that is what I have written here, and directly with respect to the modulus. So if we take this modulus, so this is nothing but ux square plus vx square, and due to the Cauchy-Riemann equations, we know that uy square equals to vx square. So this first term lead to this square of this complex, this absolute value. So this much is fine, I guess. And then for the second term, so second term we'll be using again the Cauchy-Riemann equation. So what do we know? And yeah, I hope you all know that the partial derivatives commute. So partial derivatives doesn't depend on the order with which they are taken. Yeah, okay. So that is why, let us first take the derivative with respect to y of the function ux. So that is written as uxy. So first we take the derivative with respect to x, then we take derivative with respect to y. And this will be same if we take the derivative in other order. So this will be would have been same had we taken the derivative with respect to y first and then with respect to x. So now we'll be using the Cauchy-Riemann equation. So ux's xx is vyx because ux equals to vy, and here uyy equals to minus vxy because uy equals to minus vx. So from Cauchy-Riemann equations we are left to this, and from Cauchy-Riemann equations, we are led to this vyx minus vxy, and as I have just said, so partial derivatives doesn't depend on the order, so they have to be equal. So vyx equals to vxy, so they cancel each other. So at the end of the day, we are left with f dash z modulus square, because we know that f dash z equals to ux plus ivx. So yeah, this concludes this problem also. I guess, is there any comment or any doubt? Okay, I guess that's fine. And then now we'll be doing a more involved problem. So we have to find an analytic function whose real part is given as this. So here we'll be making use of the Cauchy-Riemann equations mainly and integrating the partial derivatives. So these are the two main concepts involved. So let us try to find the vxy first, the imaginary part. So the Cauchy-Riemann equation. So Vy, as I said, Vy is ux, and then we directly calculate partial derivative of u with respect to x. So you can convince yourself that this leads us to 1. And similarly, Vx will be equal to minus uy, and by calculating partial derivative of u with respect to y, we are led to 2. So again, this is straightforward differentiations. Okay. So now we are given these two equations. So we know partial derivative of v with respect to y and with respect to x separately. So equation 1 and 2, we have these two partial derivatives of v. Now we will like to integrate these partial derivatives to obtain v. Okay. So consider 1. So we will be integrating with respect to y. So this is done by integrating as is done in real variable calculus. So integrating with respect to y, but keeping x fixed, like as if it is a constant. So we integrate y. So like consider this first term, cos x cos hy. So integration of cos hy with respect to y gives us sin hy, and cos x is treated as if it is a constant while we are integrating the y variable. So like the other terms has to be treated similarly. So integrating this factor, integrating this equation 1, we are led to equation 3. And please note the appearance of this undefined function fx. So these functions will always appear in a partial integration, because you see it is like a integration, it is like the integration constant of the single variable calculus. So the single variable differentiation of a constant is always 0. So here the partial derivative of fx with respect to y is always 0. So that is why a function which is only a function of x can always be there, and that cannot be determined by integrating only one variable. So this is why fx is as of now undetermined. Similarly, we will now integrate out 2 with respect to x, because vx is this thing. So again, similarly, now we will be treating y as a constant, but x will be, the function of x will be integrated as if it's a real single variable thing. Yes. So this leads us to equation 4. So here for a sample, so sin hy, so please follow the first term. So sin hy, so keeping it a constant, so it is sin hy, but we'll be integrating minus sin x, and we know minus sin x when integrated with respect to x gives us cos x. So all the other terms are to be done similarly. So now again here we will have gy, because yes, again here we will have this undefined function gy, undetermined function gy, because derivative of this function with respect to x will always give us 0. So we cannot determine it here. So now we have to, so now let's compare the forms 3 and 4. So we'll see some similarities and some dissimilarities. So the first three terms are same in 3 and 4, but there is difference in fourth terms, and then there are these undetermined functions fx and gy. Yes, and we see that the fourth terms in both the cases are only functions of x and y. So they are not bivariate functions. They are only functions of either y or x. So that nicely fits in the scheme of this function fx and gy. So you can guess from the forms that gy we should have gy as 2y square and fx as minus 2x square. Then 3 and 4 are consistent with each other. So that is how you have to compare to find the undetermined functions. Okay, and so by this comparison we are led to this one. So we have substituted fx and gy by comparison. So this is the final form, and then we have this integration constant c, that will always be there. So this is our final function vxy. So we get the harmonic conjugate of the u function given beforehand by this procedure. So this is the elaborate procedure to find the harmonic conjugate of a given function by means of the Cauchy-Riemann conditions and then integrating out. So now we will like to calculate the actual complex function fz. So this is ux plus ivy, and okay, I have jumped several steps, but this is nothing but straightforward algebra. Just take things common and you will find the second step. And then we know that sin x, sin x has the definition like, oh sorry, there is a typo. So sin x is e to the power ix minus e to the power minus ix divided by 2i. So the I is missing here, sorry for that. And sin hy is e to the power y minus e to the power minus y divided by 2. So we have to substitute these definitions in place of sin x, y, sin x, cos hy, cos x, and sin hy. So, and we all recognize that x squared plus 2y xy minus y squared, this is nothing but z square. So this is x plus iy whole square. So after substituting these definitions, and there are several terms that will be cancelled and that can be combined together. So that gives us this sin z plus z square multiplied by this constant factor. So this is the final answer. So in this kind of problems, so you have to express the final answers as a function of z, because at the end of the day what we are looking at fz, which is a function of z. So you have to perform all these final steps. So that is that. So sin z plus z square. So yeah, that was a little more involved problem. So yeah, so is there any doubt? Okay, so you say that you do not know sin hy formula. So yeah, so you can treat this like a definition of this sin hy formula. So you can find these at any standard textbook, or for that matter Wikipedia also, but yeah, these are standard formula, or rather standard definition. So you see, okay, one thing. So if you are, uh, uh, if you are familiar with the sin x formula, so this is nothing but, well, this looks pretty similar, isn't it? So just substitute ix by y. So since there is no I here, so this is just e to the power y, but not e to the power iy. Since no I is here, so this is that is why this is a sin h. So you can treat this as a shortcut. So if there is no I, then here it is sin h or cos h. So yeah. Okay, then I'll be moving on to the most involved problem of this session here. So I guess this thing has been taught already, right? So what is a vector field, what is equipotential line, and all this. Okay. So, let's consider electrostatics. So in electrostatics, we are given, or rather, yeah, there is an electric field and electric potential, right? So we know the formula. So electric field is the gradient function of the electric potential, right? I hope you are all familiar with that. So this is the same concept here. So this is a vector field. So vector field means it's a vector, and so there is two components. One along x-axis. So x-axis direction is I cap, and another along the y-axis. So this direction is j cap. So these have these two components, and so consider it like an electric field. So given, let's say this F is an electric field. So if F is an electric field which has this form, so which potential gives rise to this electric field? So we would like to find that potential. And in 2 dimension, there is a speciality because of the existence of these complex analysis things. So these things can be done much more easily and elegant way. Okay. So first we'll be doing some, I'll be telling you some definition. So the thing that I said, if you have a potential and then you take the gradient of that potential, you get electric field. So similarly, but since that is a electric field is a real vector field, so the potential that will be giving rise to that will be a real function. So as simple as that. But here we'll be solving that problem much more elegantly by use of the complex potential. So the complex potential, so which is defined like as an analytic function of z, is given by this thing, usual phi z equals to u plus iv. Okay, and the real potential that I was saying, the real potential is ux. So the real potential is the real part of this complex potential. So ux is the electrostatic potential that gives rise to an electric field. Think like that. So here it is written, the function uxy is the real or physical potential. So yeah, like the definition. So fx, so here f to the power x you may think, but it is the x component of this vector field. So x component of vector field is given by partial derivative of the real potential with respect to u, and similarly fy equals to uy. Thus we have ux equals to x by square. So just read from this given given vector field, and uy is that the y component of the vector field. Now again we'll be integrating. So as we did in the previous problem, so we'll have to integrate out x and y. So in the first line, let us first integrate x. So this is straightforward. So you can see that log x squared plus y squared by 2, its partial derivative is ux, that is given here. So gy is the undetermined function, as I explained in that problem, and similarly for uy. So this is nothing but one variable integration. So now let us compare fy and gx. You see the first terms in both cases are already same, and then the first terms in both the cases are already same. So we are left with this undetermined thing, fx and gy. So there is nothing to compare with them. So we conclude that fx and gy are nothing but two undetermined constants, and both are equal. So after this comparison, we are left with this. So this is the physical potential. uxy equals to half log x squared plus y squared plus constant. Okay. So this was our real potential. So the equipotential lines are defined as uxy equals to constant. So just as in the case of electrostatics. So equipotential means the curve along which a potential is constant. So straightforwardly, we put uxy equals to constant and take the exponential in both sides, and conclude that the equipotential lines are actually circuits. X squared plus y squared equals to c1. So yeah, in this case we have circles as the equipotential lines. And now will be, so to find the whole of the complex potential, we need to find its imaginary part also. And as I said, phi z is defined as a analytic function of z. So that means it has to satisfy the Cauchy-Riemann equations. So then we use the Cauchy-Riemann equation. So Vx equals to minus Uy and Vy equals to Ux. So Vx, which is minus Uy, and Uy was the y component of the vector field. So just substitute here, and we get Vx equals to this, and similarly Vy equals to this, x by x squared plus y squared. Okay, and then, well, how can you see that? Don't know, but integrating out x and y gives us tan inverse y by x. I hope, yeah, please don't be intimidated by these integrations, because as I said, just treat one variable as constant and do the integration with respect to other, and that will lead to results. Okay, and that will lead to results. And so again there is these two undetermined functions, but there is nothing then to compare with, so they are constants. So they have to be equal to each other, but one is function of x and the other is function of y, so they better be constants. So then we have the imaginary part as tan inverse y by x. Okay. So, and the streamlines are defined as Vxy equals to constant. So this is the definition. So in this case, they are of course tan inverse y by x equals to constant, so that gives us y by x equals to constant. So this is the equation of streamlines, so we recognize them to be straight lines. So yeah, so in this case the equipotential lines were circles and streamlines were straight lines. So streamlines and straight lines, they have this property that whenever they intersect with each other, they intersect mutually orthogonally. So if you draw tangent at their points of intersection to both curves, so those two tangents will be perpendicular to each other. So that is what is meant when we say that two curves are mutually orthogonal. Okay, so that is one property of streamline and equipotentials. So finally, after all these calculations, so we are now in a position to deduce the complex potential. So phi z equals to ux plus I vy. Just substitute here, and we'll see that this is the log z, because log z is log of absolute value of z plus I into argument of z. So finally our complex potential is log z. So that answers this question. So like if we want to connect with electrostatics, so such a potential is generated by an infinitely extended uniform line charge. Okay, so that is just a side information, but yeah, that is the process to find the equipotentials and streamlines and then the complex potentials. So yeah, that was a somewhat involved problem. So yeah, is there any question? How did log z come? So log z is actually, this is the definition of complex logarithm. So I said, so you can consult a textbook. So okay, so you know the formula. So z equals to, in the polar form of complex numbers, so z equals to r multiplied by e to the power I theta, right? So r is the absolute value of z and theta is the argument of z. Z equals to r e to the power I theta. So now if you can take logarithm on both sides. So what are you left with? Logarithm of z equals to logarithm of r into e to the power I theta. And we know logarithm of xy equals to log x plus log y. So what we have? Log z equals to log r plus log e to the power I theta. And log e to the power I theta means it just I theta. So we are left with log z equals to log r plus I theta. So, and theta is tan inverse y by x. So that is the argument of the complex function. Okay, and r is root over x square plus y square. So that is how you can derive this formula. So this real function leads to the complex logarithm. Yeah. Well, so I am already. So no, what do you mean by natural logarithm? Is it with respect to the base 10? I don't think so. So this is the logarithm with respect to the base e. And I guess the natural one is defined with respect to the base 10. Yeah. In this course, all the logarithms will be with respect to base e. So that is why it is written Ln. Well, now another, the final problem of the session, and it's a similar problem. So given a vector field, we are again asked to find the equipotential lines and streamlines and the complex potential. But now we'll take a different and shortcut approach. Okay, so as I just explained in the last question, so the x component of the vector field, so yeah, so consider the real potential uxy. So as I just explained, so the x component of the vector field is nothing but partial derivative of the real potential with respect to x. So ux is equal to uh, x component of the vector field, and uy is equal to y component of the vector field. Okay, that part is fine. And then if we combine this fx minus I fy, so yeah, please look carefully at this combination. So fx minus I fy, so combination of the x and y components. So this is nothing but ux minus iuy as as per definition, and then by the Cauchy-Riemann conditions, this is nothing but ux plus ivx, because vx was minus uy. Thus, and now we recognize ux plus ivx is nothing but the complex derivative of an analytic function with respect to z, and our complex potential was u plus iv as we defined in the last problem. So ux plus ivx is nothing but the derivative of the potential, the complex derivative of the complex potential. So phi dash z is ux plus ivx. This is the definition of complex derivative, and which we see it is fx minus ify, this particular combination. Okay, fx minus ify. So now this is the starting point of the shortcut. Thus, in this problem we have the in this problem we have the following complex potential. So phi dash z equals to y minus ix. Just substitute from what is given in the question. So fx is y and fy is x. So we substitute y minus ix, and this is nothing but minus iz. So phi dash z is minus iz. So this is an easy integration. So phi z is minus I z square by 2 plus some constant which is always there. So now we directly calculate the complex potential, which is phi z equals to minus I z square by 2. Okay, and then to find the to find the equipotential line and the streamline, we have to separate out the real part of this complex potential and the imaginary part of the complex potential. So when we write z equals to x plus iy, we find that uxy equals to xy and vxy equals to y square minus x square by 2. So simple as that. So the equipotential lines, which are yxy, uxy equals to constant, is given by xy equals to constant, which is a hyperbola, and the streamlines are vxy equals to constant. Okay, and so yeah, and streamlines are vxy equals to constant. So we can see the equation of streamlines are y square minus x square equals to constant. So that is another hyperbola. So, and we know that these two types of hyperbola are orthogonal to each other. So respecting the properties of the equipotential line and streamlines, these two curves xy equals to constant and y square minus x square equals to constant again intersect each other orthogonally. So yeah, that is that. So you see in the previous problem I needed 3 pages to explain, but here I need only 1.5 page to explain. So this is really a shortcut and easy method. You just have to use this combination phi dash z equals to fx minus ify, and you then have to uh, express the function fx minus ify as a function of z only, and then you can you can do the integration with respect to z, and then you get phi z, and then you will just write the real part and complex part of the complex potential in terms of x and y, and then simply you get the equipotential lines as the constant and as the real part, and streamlines as the imaginary part. So yeah, that solves this problem. So yeah, that concludes the discussion of the problems. What is the constant from well, okay, it is still there, but I have chosen to not write that. So you can always add constants to potential. So what really matters, as you know in physics, so what really matters is the difference between the potentials, right? Not the potential energy themselves. Yeah, this is the same thing. So the constants, the numerical constant doesn't really matter. But for, I mean, to be correct mathematically, you need to always write that. Okay, yeah, you can say that I have made a mistake by omitting them. Yeah, okay. But when we do finally our goal is to write the equipotential lines. So then you see that constant that I haven't written here, you can think that to have been absorbed in this constant. And similarly for the streamlines also. Yeah. Ah, okay. So yeah, that's that. So if there is any other question, please feel free to write. And if not, then I will end this session. Yeah. Okay, then I guess there is no more questions. So bye. See you next week. And meanwhile, please practice problems and submit. Yeah. Okay. Bye.